Hey, chemistry. Welcome to talking about moles and volume. We have talked about moles and volume before, so I want to start with just a recap of what we've talked about before and then move on from there. So the moles to volume conversion that we've talked about before is summarized in this little diagram that we've also recapped. So notice here's our moles and here is our liters of gas. So the moles to volume conversion that we've talked about is right here, and this is molar volume. But remember, it's only for a gas. Molar volume cannot be used unless the state you're talking about is a gas. It can't be used for liquids, it can't be used for solids, and it can't be used for aqueous things. It can only be used for a gas. So we're going to talk about one more conversion today between volume and moles that is going to kind of expand our ability to convert within certain phases. Okay, before we do that, I just want to recap though our figure here. Remember, this diagram can help us keep track of our conversion factors. Right now, it's helping us keep track of 3 conversion factors. We have particles, and they've given you some examples of what your particles could be. It could be atoms, could be molecules, could be formula units. Your particles aren't limited to those. It could also be ions, could also be golf balls, could also be donuts or elephants, right? So anything that's a particle, if you want to talk about one group of that particle, we call this very large group a mole. And the conversion between particles and moles is right here. It's Avogadro's number. So it's 6.02 times 10 to the 23rd particles per mole. And then we have our grams or our mass to moles conversion here as well. If we want to convert from mass to moles, we're going to use molar mass. Remember, we get molar mass from the periodic table. And then, of course, we have our moles to volume. We're going to use our molar volume, 22.4 liters per mole. So units are really, really important to us. One more thing before we move on in here on this note of units. Notice they don't actually give you your units in this diagram. They're only giving you numbers. So you have to know the units. Same thing with molar mass. If you pull off the molar mass of carbon from the periodic table, 12.01, that number is not very useful unless you also know the units. I'll give you a hint, it's not grams. The molar mass of carbon is 12.01 grams per mole. So don't drop your units. Remember, all 3 of these are going to have 2 units, which make them a conversion factor. In order to be a conversion factor, you have to have 2 units. All right, so we have talked about molar volume converting from liters to moles for a gas only. The conversion factor we're going to talk about today also goes from volume to moles, but instead of being for a gas, it is for an aqueous solution. So for something dissolved in water. And when we talk about the moles dissolved in an aqueous solution per unit of space, or moles per volume, what we're talking about is called molarity. So molarity, we represent it by a capital M, tells us how many moles of a substance are dissolved in a certain volume of water. So you're going to have moles of the thing dissolved That's called a solute. Fun fact of the day. Per volume total. So that would be the water plus the thing dissolved. Okay, so that's what molarity is. Now let's take a closer look at molarity before we talk about how to use it. So you can actually add a line here between volume and moles. I guess it would, it's liters of something that's aqueous, and that line would be represented by molarity. So let me give you a couple examples here. Okay, in this picture, you can see I have a couple different solutions. All these solutions are solutions of glucose. So what that means is that glucose has been added to water and dissolved in the water to make a solution. You can see they tell you the moles of glucose and the liters total that you have. Moles of glucose, liters total that you have. Moles of glucose dissolved, liters total that you have. So if you take these amounts and you divide them, remember molarity we just said is moles of thing dissolved over the volume total. So we can actually calculate the molarity of all these solutions. 0.06 moles of glucose per 0.06 liters total gives us a 1 molar solution. Over here, we can do the same thing. 0.18 moles of glucose per 0.06 liters of solution gives us a 3 molar solution of glucose, and then 0.06 moles of glucose per 0.02 liters total gives us a 3 molar solution. Notice they tell you here, I'm switching between the word molarity and the word molar. And so they tell you here how to read it. 3M is read 3 molar. So then you know you're talking about this. So notice a couple things here. First of all, when we talk about molarity, really what we're talking about is concentration. How many particles are in a certain amount of space. And you can see that. Notice they take a part of a droplet, right? And they blow it up for you. And you can see that a 1 molar solution has less particles in that droplet than a 3 molar solution. A 3 molar solution is going to have more droplets, more particles in that droplet. So really what they're telling you is a measurement of concentration. Now we've dealt with concentration before. We've dealt with concentration in terms of density. Density is also a way to measure concentration. Now, do you remember how to calculate density? So density is mass per volume or grams per liter. Notice that it's really similar. Density is grams per liter. Molarity is moles per liter. So density is the mass in a certain space. Molarity is the number of counted particles in a certain space. So they're very similar, but one's dependent on mass and one's dependent on counted particles. So they're a little bit different in that way as well. Another thing to notice, the amount that you dissolve by itself does not determine the molarity. Notice in solution number 4, we're dissolving 0.18 moles of glucose. In solution number 5, we are dissolving a third of that, 0.06. Right? We're dissolving a lot less glucose in that 5th solution when we're comparing to the 4th solution, but the molarity comes out the same. They're both 3 molar, 3 molar. So why is that? How can we dissolve less glucose but come out with the same concentration? Well, you may notice here that not only is the amount of glucose less in solution 5, but the volume is less as well, right? The amount of glucose is a third in solution number 5. The volume is also a third in solution number 5. So molarity is not a direct measurement. Molarity is a ratio. We love ratios. Ratios are amazing and they carry us through chemistry. Molarity is a ratio, so is density, right? If you decrease the volume, you're going to decrease the number of particles you have, right? But the particles per volume space, that ratio of particles to space, will stay constant. So molarity is a ratio, as we can see in these things. All right, not only is molarity a ratio, molarity is a conversion factor. So molarity is moles of thing dissolved over liters total. Notice 2 units. The top is equivalent to the bottom and it's a fraction. That makes it a conversion factor. So what would we use it to convert between? We'd use it to convert between moles and liters for an aqueous solution. So molar volume is just for gases. Molarity is just for aqueous solutions. It's a conversion factor between moles and liters, which means that molarity is constant no matter what part of the volume you take it out of. If we take this drop, we're going to get a ratio of glucose to volume of 1 to 1. If we take this drop, we're also going to get a ratio of 1 to 1 when we're looking at glucose to volume. So that's what this 1 molar is communicating, that the ratio of glucose to total volume is a 1 to 1 ratio. What's the ratio for this solution, for solution number 4? Glucose to total volume, it's going to be a 3 to 1 ratio. And so that also explains why it stays consistent. 0.18 to 0.06 is a 3 to 1 ratio. 0.06 to 0.02 is a 3 to 1 ratio, right? Molarity is just a ratio that communicates concentration. So as this other conversion factor that gets us from volume to moles for an aqueous solution, we can use it to convert between volume and moles for aqueous solutions. Let me give you an example of that. All right, think back to our iodine clock reaction. Remember doing this lab? We're dealing with the 2 forms of iodine here. One form of iodine is colorless. One form of iodine is this like dark bluish, blackish color. And then we used vitamin C to suppress changing from one form of iodine to the other, right? Vitamin C kept our iodine form in the clear form. Once the vitamin C was done, we saw this change a couple minutes later to a second form of iodine, which was colorful. So this clock reaction can also be done with other compounds. So vitamin iodine, peroxide, and vitamin C is one group of compounds that will give us a clock reaction like this. Well, mercury chloride is another solution. And one of the points of this lab that we talk about is that the vitamin C reaction is green, right? It's earth friendly. Everything we dump into the drain isn't going to harm our waterways and our farmland and the earth that it goes into, right? Well, not so with mercury chloride. You got to be really careful how you dispose of mercury chloride so you don't cause mercury poisoning in wildlife, especially in streams. And so we can look at this mercury-based clock reaction, and we can do calculations beforehand of how much mercury we would actually be disposing of every year. So in order to do that, we need to know what the molarity is of our mercury chloride solution. And our mercury chloride solution that we would use for this experiment is a 0.01 molar solution. So that's 0.01 moles of mercury chloride, mercury 2 chloride, over 1 liter of solution total. And in order to do this experiment with mercury chloride, we would use about 150 milliliters. So remember, molarity is a conversion factor. It helps us convert between moles and liters. Well, my measurement for this specific lab, or my given for this specific lab, is 150 milliliters. So I'm going to convert that into liters. 150 milliliters in liters is 0.150 liters. Okay, so if I use that, if I use my given 0.150 liters, can I convert that into moles? Go ahead, pause the video and see if you can do that. All right, I'm going to set up my conversion factor. I know I want to end up with moles. How many particles of mercury chloride am I going to end up with? Am I going to end up putting in my stream? So I want to convert it. I want to get out of liters. I'm going to put liters on the bottom. Remember, whatever's on the top automatically goes on the bottom so that it will reduce out, and I'm left with moles. Now that I have my unit set up, I'm going to plug in numbers, 0.01 moles per 1 liter. Liters reduces out, and I can do this calculation. 0.15 times 0.01 divided by 1 comes out to be 0.0015. 0.0015 moles of mercury chloride. So if I did this lab with mercury chloride instead of with vitamin C, for every lab group that rolls through here, I would be having to dispose of 0.015 moles of mercury chloride. Now, that may not mean a whole lot to you in terms of moles, but remember, once you get into moles from volume like we just did, now you can go into particles. We could figure out how many atoms of mercury we would be putting into the environment, or you can go into mass. We could figure out what the mass of mercury is that we'd be putting into the environment. So getting into moles is really powerful. And this is exactly how you would use molarity to help you get to that central hub of moles. Okay, so molarity is another conversion factor. This would be a great one to make a flashcard of. You can put a little information on the back. You can put an example fraction on the front, so you remember mercury can help us get between volume and moles when we're talking about aqueous solutions. It's not going to help us with liquids. It's not going to help us with solids. It's not going to help us with gases. It will help us with aqueous solutions. Okay, so let me know what questions you have on this. We will practice this together when I see you in class next.